This video discusses one very important subspace associated with any linear map called the kernel of a linear map. For this video and the subsequent video, we'll be, how should I say, we'll be concerned exclusively with maps which are linear between vector spaces. So again, linear map means linear function, and if I ever neglect to say so, you can just assume that any map we write down in this section and the next are definitely linear maps. So, our first definition, let L be a map from V to W which is linear. Then we say that L is one-to-one, or I will often write just one-to-one instead of writing out the words, if the following condition is always true. If, whenever x and y are distinct vectors, we have Lx and Ly distinct vectors. Or you can turn this around and state what is called the contrapositive. You could equivalently say that L is one-to-one if, whenever Lx is equal to Ly, we must have x equal to y. Let's look at an example. For our first example, let L be the linear map from R2 to R3, such that L maps the vector AB to the vector A plus B, A minus B, and B. Then I claim that the map L is one-to-one. To verify the claim that L is one-to-one, we can use this criterion. That is, we assume that Lx is equal to Ly and show that x must be equal to y. So here's our assumption that L of one vector is equal to L of another vector. And then this assumption becomes the following. Equate this vector with this vector. These, after all, are the images of the vectors under L. And equating these two vectors gives us the following linear system right here. And then if you solve this system, I'll let you solve it, you can immediately see that B is equal to D. And then if you substitute B equals D into either of the first two equations here or here, then you can obtain A is equal to C as well. And so you can show that under the assumption that LAB equals LCD, you can show that AB must be equal to CD, and hence this map L is one-to-one. This definition may seem a little familiar because we've seen it before. In fact, we saw it back when we defined the notion of an isomorphism from one vector space to the next. One of the defining properties of isomorphism was that the function which established the isomorphism was linear. And now we can define the kernel of a linear transformation. So the data for this definition is the following. We have a vector space map, or a linear map, L from V to W, and we define the kernel. The kernel of L is the following. It's all x in V that are sent to 0 by L. So here's the condition. It's all of the x in V again, such that L of x is equal to 0. Here's a very rudimentary picture to help us understand what the kernel is. So it's just everything over here in the domain. Here's the map L, which goes from V to W. It's everything here in the domain, which is sent to 0 in the range. Let's look at one quick example and find the kernel. Let L be the map from R3 to R2, which maps XYZ to XY. So you may be able to imagine what this map does with a picture. This takes any point in R3 and essentially just forgets the z coordinate, so it projects it down to the x-axis. Take any point up here, maps it down here. If I take any point below the xy plane, it just maps it up to the xy plane. I'm sorry, I think I said x-axis. I didn't mean xy plane. Right, so this map is projection onto the xy plane. So now let's find the kernel, but perhaps it's useful to think about what the answer is before we write it down. The kernel of this map will be all of the vectors in R3, or in space, which map to the 0 vector in R2. Now, where is the 0 vector in R2? Well, let's focus on R2. It's the plane here. And the 0 vector in R2 is just the center of R2 right here. So if our linear map does this thing of projection, then what are all of the vectors which are mapped to the red dot to the origin by projection? They should be precisely all of the points on the z-axis. all of those are mapped to 0 above, and all of those are mapped to 0 below. So the kernel of this map, the vectors in R3 that are mapped to 0, should simply consist of the z-axis. If you can justify that intuition algebraically, let xyz be in the kernel of L, and we'll see if we can describe xyz. So if xyz is in the kernel of L, then by definition, L maps xyz to 0, and that's what we see going on right here. So what's the definition again of L of xyz? Well, it maps xyz to xy. So we know that xy must be equal to 0, 0. Then equating this vector and this vector, we see that the x-coordinate must be 0 and the y-coordinate must be 0. That's that condition. And therefore the vector up here, which we assumed was in the kernel, must be of the following form: xyz equals 0, 0, z. Well, that's precisely the z-axis. So it's true, the kernel of this map is just the z-axis in R3. Let's pause to make this helpful remark. Remember, we proved a proposition about linear maps, and that proposition was that linear maps always map 0 to 0. That's this condition right here. If L is a linear map, then L of 0 is equal to 0. Here I've carefully labeled. If L is a linear map from V to W, I've labeled the 0 element of V by 0 sub V, and similarly for 0 sub W. So what do we know? We know that the kernel always contains something. At least 0 goes to 0. And if we were to draw this very rudimentary picture again of vector spaces V and W and the linear map L going from one to the other, here's 0W over here, we're always guaranteed that at least one thing goes over here. But we're interested also in the cases when other things may go over here as well. Maybe lots of other things. For example, in the previous example, we saw that it was the whole z-axis which was mapped over to 0. So let's make a few remarks about the kernel. Suppose we have two vectors, v1 and v2, in the kernel of the linear map. Well, then again, by definition of the kernel, since v1 and v2 are in the kernel, we know that L of v1 and L of v2 are both equal to 0 in W. So we can add v1 and v2, I'm doing that right here, and then apply the linear map L to the sum. Now, since L is linear, I know that L of v1 plus v2 is L of v1 plus L of v2. That's one of the properties of linearity. Each one of these are, of course, equal to 0, 0 here and 0 here, and of course the sum of 0 plus 0 is 0. So what have we shown? We've shown that if v1 and v2 are in the kernel, then their vector sum is in the kernel as well. In a similar fashion, we can show